In this chapter, we want to start exploring the structure of the atom. And to do so, we need to first talk about the elements of the periodic table, a little bit more so about their development. And initially, right, in ancient Greece was where some of the discussions about what matter was made of initially took place. And they initially had four elements, right? They had earth, air, fire, and water. And they reasoned that everything that existed could be made up of a combination of these four elements. But with just a little bit of thought, you can see why this might need some refining. And that is, if I combine different types of earth, in other words, different types of soil, with water, then I'll get different types of substances out, maybe such as clay, mud, or various other types of things. And then to compound the issue, what's the difference between mud and rock, and things like that. So these four, while an initial attempt, were not terribly robust in their overall descriptive power. And it was actually an ancient Greek who also, as a result of these types of observations, coined the term the atom. And he reasoned that an atom, and by the way, an atom means an indivisible particle, okay? It's an indivisible thing. And he reasoned that maybe, say, if I take a piece of wood, right, and I cut that piece of wood, and I chop it in half, then I have two pieces of wood. And if I chop one of those in half, then I'll have two more pieces of wood here, and I can keep chopping them in half and so on and so forth. And sooner or later, I'll have to reach a point at which there is no more single piece of wood, just the things that wood is made out of. And this is the idea behind the atom. So he reasoned that there had to be some fundamental, smallest thing that was called wood. And then if I broke that down any further, it must be made up of even smaller things and smaller things and smaller things until you reach the point at which you can't split something any further. And that was the idea behind the atom. What's the smallest thing that matter can be before it is indivisible, before I can't separate it anymore. And so that was where the idea of the term atom came from. And if we fast forward a few hundred years, well, several hundred years, maybe 1,000, 1,500 years or so, if we fast forward that far into the future, we would go into the Renaissance. And during that time was when the initial scientific revolution was happening. Newton was formulating his laws of motion. Galileo had performed his experiments with gravity. And chemists were also starting to learn some things about chemical reactions. And one of the basic questions that had been asked was, let's say I set a log on fire, and we know that smoke is going to come up off of the fire. And one thing I can do is measure the mass of the log before the fire, and then measure the mass after the fire. And without too much surprise, we can say that the mass before the fire is greater than the mass after the fire. And this is common knowledge to anybody who builds bonfires to cook hot dogs with, and so on and so forth. And initially, people were puzzled by this, and they said, well, maybe mass just isn't conserved during chemical reactions. They did know that fire was a chemical reaction, the reaction between oxygen and air, or carbon and oxygen, rather, carbon and air, as is exposed to oxygen. And as this process occurs, it releases all this smoke. And it wasn't until people realized that the smoke and air also had mass that they were able to take the masses of the what we would call the reactants, the mass of the log itself and the mass of any of the air around the log. Now, of course, you can't go outside and just measure the mass of the air around the log. You have to do this in a controlled lab. But they could do it. They could take a known amount of air and react it with a log and set it on fire. And then they could measure the mass of the log afterward and measure the mass of the particles in the air around the log. And then what they found was that, yes, indeed, mass is conserved. If I take the total mass of my log before and all of the air before, and then I take the mass of my ashes and the mass of my smoke and add those together, then I get the same thing. And so the mass before the combustion reaction is indeed the same as the mass after the log combustion. And that led to the conservation of mass, the idea that mass can neither be created nor destroyed. Right. So fast forward another few years, and this was only about 10 or 15 years or so, and a man by the name of Dalton comes along and realizes that all chemical reactions occur in the same proportions by amount of reactants. So all chemical reactions require a specific ratio of reactants. Okay, so what that means is for any given chemical reaction will use the exact same ratio of its reactants, no matter how much of the reactants you actually have. For instance, as an example, if I want to make H2O, then that means I'm going to have 2 hydrogen atoms for every 1 oxygen molecule, or atom, actually. And by mass, though, even though I only have 2 hydrogen atoms for every 1 oxygen atom, it turns out that oxygen is so heavy that this occurs such that I need, for every 1 gram of oxygen that I have, I need 8 grams of hydrogen. Okay? And it doesn't matter how much oxygen I start with, however much I start with, I'll always need 8 times that of hydrogen to completely react all of the oxygen and turn it into water. As another example, let's consider what happens when we want to make some carbon dioxide. So carbon dioxide is 1 atom of carbon plus 2 atoms of oxygen, and that makes CO2. Now, let's assume that I start out with 30 grams of carbon. Okay, so that's the mass of my carbon, all right, and maybe we should write this as the mass of my carbon, maybe M sub C, and I want to know how much oxygen will it take, how much mass of oxygen will it take to completely combust with this amount of carbon. Well, something we can note is what we call the molecular weight. And the molecular weight was actually kind of born out of this type of analysis. Early on, back in the 17 and 1800s, people didn't necessarily know, right, how much an individual atom weighed. And now our modern idea of molecular weight is in terms of hydrogen. Everything is compared to the hydrogen atom. How much heavier than hydrogen is it? But they did know their relative weights. So they didn't know the exact weight of one hydrogen atom per se, but they did know that, for instance, carbon, the mass of one carbon atom was equal to about 12 times the mass of a hydrogen atom. And the mass of an oxygen is about 16 times the mass of one hydrogen. And so if I have CO2, then I need 2 of these guys. And so in CO2, I can write down the ratio of my oxygen to carbon atoms as in terms of the masses of the hydrogen. So the oxygen, I'm going to have 2 atoms, and they're both 16 times the mass of hydrogen. And I'm going to have 1 carbon atom, which is 12 times the mass of my hydrogen. And so this turns into 32 divided by 12, which reduces to 12, which reduces to 8/3. What that means is that for every 3 grams of carbon, I need 8 grams of oxygen for this particular reaction to occur. Okay, so I need 3 grams of oxygen, or I'm sorry, if I have 3 grams of carbon, I need 8 grams of oxygen. And so, if I look at my oxygen over here, that should have been M sub 0. Let me erase that. And so M sub 0, well, if I have 30 here, then how much do I need? Well, I need to multiply this by 10, since 3 times 10 is 30, therefore 8 times 10 is 80. So I need 80 grams of oxygen for my mass, and that will completely react with 30 grams of carbon. And it was through these types of experiments where people were noting how reactions worked and with what elements that we started to build an overall picture of what each element was, how heavy it was, what its properties were. And this led to the periodic table. Now, the first periodic tables were developed in the 1800s, and most notably by a man by the name of Mendeleev. He was Russian, if I'm not mistaken, and he essentially tried to start ordering the elements into similar properties that they shared. And he was the first one to kind of arrange things in the form that we have now, where hydrogen is on one side of the table, helium is on the other side of the table, and then you have lithium and beryllium, and then you have a bit of a gap in boron and carbon and so on and so forth. And essentially, from the studies of these chemists, some of these patterns began to emerge that atoms like hydrogen and lithium and sodium and calcium, or potassium rather, all kind of reacted very similarly. Right? And then beryllium and magnesium and calcium also reacted very similarly. Helium and neon and argon didn't seem to want to react at all. Now, at this point, helium hadn't been discovered. It would be a little bit down the road. But then again, also things like fluorine and chlorine also were known to be highly, highly reactive. But then things like oxygen and silicon also shared very similar properties. So it was as a way of forming these elements into groups that shared similar properties that our modern periodic table emerged. So I really encourage you to start to look at the periodic table as we go through this chapter, but this also raised some questions as to why these atoms were very, very similar. We didn't know what the structure or the atomic properties of atoms were. We hadn't probed into what an atom was made up of yet. All we knew was that some of these atoms shared some very, very similar properties. But there was the underlying question, why were these atoms similar? And that is the question that we will answer in the next video. So stay tuned until then.